Okay, so today we're starting on the last module for this course, which is searching and sorting. It'll continue almost until the end of the semester, but what time permitting, we'll do other topics like graphical user interfaces, maybe some database connectivity, or like parallel programming or something like that. Searching and sorting are two basic fundamental operations when it comes to processing data. Just like, addition and subtraction and multiplication, those are the basic operations of math. Whenever you process data, these two operations are fundamental, right? They're either the beginning, or they're a subroutine for some other algorithm or some other process, or they're in and of themselves the important things that you want to do. Like you want to find that needle in a haystack. It forms the basis of pre-processing for multiple steps in different algorithms, because a lot of algorithms will assume that the input is in a certain order in order to be greedy and take the best solution first or something like that, right? Another reason that we look at these things is because there's a huge variety of algorithms out there. If you just look for searching or sorting algorithms, most likely on YouTube, you'll get 50 million different videos, some of them visualizing various sorting algorithms. Some of them have like dancers dancing the algorithms and demonstration and a bunch of stuff like that. There are literally a dozen different sorting algorithms. When it comes down to it, though, you probably only want to use a select few, right? But in any case, we're going to start looking at things in more general, right? We're not going to look at it in terms necessarily of just C, because these algorithms are universal. You can implement them in Java, you can implement them in C#, you can even implement them in whatever language you want. In fact, you can even have dancers simulating the algorithm, right? So what we need first is the notion of what an algorithm is, right? If you pull out your dictionary, Webster's dictionary, then you'll get some sort of definition that looks like this. An algorithm is a finite sequence of operations that define a computational process for solving a problem, right? Now, that's not the math definition, right? The math definition would, of course, be either Turing machines or lambda calculus or something like that. But this definition is good enough for us because it gives us an idea of what an algorithm is, right? All algorithms must be correct and finite, right? Otherwise, if they're not correct, they're still an algorithm. It's just an algorithm for a different problem. It doesn't solve the problem. It has to be finite because you need to have it execute, and terminate execution at some point, right? Otherwise, it goes on forever. Do understand the difference between algorithms and problems. Algorithms are the things that solve the problem. The problem in this case, for example, is sorting. Given 10 things, I want to put them in order. That's the problem. There are lots of algorithms to solve that problem. Selection sort, insertion sort, quick sort, merge sort, tim sort, right? We'll look at a few of those. But those are the actual algorithms that solve that problem, right? We can express an algorithm using pseudocode. So what does pseudo mean? Fake, right? Not real, right? Fake code. And so we're going to write pseudocode eventually here after we take a first stab at the first problem of searching, right? We'll go over the rules for pseudocode, and I put rules here in quotation marks because there are no rules for pseudocode. If you had a rule for pseudocode, guess what? That's called a programming language, right? Exactly. There may be more than one correct algorithm to solve a problem. So given two or more algorithms that are correct, now we come to a question of which one should we use, right? You need to then decide which one to use based on its complexity, right? The efficiency. Efficiency, right? If I have two sorting algorithms and they both solve the problem, they both sort the array of elements or whatever you're trying to do, right? How do I know, should I use that one or should I use that one, right? That's where algorithm analysis comes in, where you have to actually look at the algorithm. How much work does it do? How much work does it do with respect to the input size? And then you make a choice. That one's more efficient, and I can prove it because I looked at it from the perspective of an algorithm, an abstract notion of what you're doing, rather than actual C code, which I benchmark on something. Take that C code, move it over to a different system, and you have completely different benchmarks because you have completely different hardware. I don't want to look at it from that angle. I don't want to look at it from, oh, well, I can always improve this algorithm by upgrading my hardware. That's not how it works. The algorithm is the algorithm. The algorithm is just as inefficient as, if it's inefficient, it's just as inefficient now as it was, say, 2,000 years ago. Or it's just as efficient now as it will be 3,000 years from now. Right? It's just that the hardware that you run it on is faster. So we want to look at them independent of any particular machine. Right? How many operations are you actually performing? So to get into this and to motivate it a little bit, let's go ahead and talk about that first part. Again, it's searching and sorting. So let's go ahead and talk about searching, which you've already done. Okay? But before we do that, let's understand what we mean by searching. What does it mean? Right? So I'll ask some questions here. What are you searching? Right? So okay, so you're searching for some. If there's only one, is there really a search? Here it is, right? But I'm searching for a needle in a haystack. What is our haystack with respect to, say, C? An array, right? Array. Right? Other programming languages have other data structures that hold collections, right? Lists, right? Sets, maps, etc. If you have any Python programming background, they have dictionaries, which are nothing more than neutered maps, by the way, right? So what are you searching for, through, right? That's one question. What are the elements that you are searching among? Right? Integers, right? Doubles, characters, right? Or now that we're into structures and user-defined types, are you searching for a particular airport, right? A team, right? Et cetera, et cetera. Right? So what are the elements that you're searching for? How are you searching? Right? So, for example, you can be very, very specific and say, suppose that I have a student object or a student structure like you had in your labs the other week, right? What are some ways of searching for a student? By name? What's another way of searching for a particular student? If you're an NUID, right? Or a social security number, right? Or maybe a GPA, right? Whatever data you have, you can search on, right? Maybe a combination of these. I want to search for everybody whose name starts with a C and has a GPA of greater than 3 or something, right? So how are you searching for a particular element, X, right? I've got my needle that I want to, and I want to find the matching needle among the haystack, right? I'm searching for a particular element. I'm searching for that student with NUID 1234. Right? Or are you searching for a maximum or minimum element? Right? That's also a search problem. Right? I want to find the student with the highest GPA. Or I want to find the student whose name comes last in alphabetic order, right? The minimum element. Right? Or another one that you've seen before, the median, right? Another statistic. Or generalizing that, the kth order statistic, which you probably saw in lab 6, or lab 7, excuse me. Right? Find all instances of X, the first instance of X, right? The last instance of X, right? All of them, et cetera, right? So exactly how are you searching? Take every single combination up here, and that's a different function, right? What I want to do is I want to divorce myself from that entirely. What I want to do is I want to look at this problem generally, okay? But before we do that, let's actually go ahead and think about what it looks like over here in C. If I've got, say, an integer array, right? 4, 8, 2, 9, 4, 1, 3, 1, 2, 3, 4, 5. There we go. There's 8 elements in there. Int n is equal to 8. Right? So this is an integer array. This is one of those particular answers to to all these questions. What are you searching? I'm searching an array. Well, what are the elements that you're searching among? Integers. And how are you searching for it? Let's say for a particular element x, which we'll call a key, int key. Let's go ahead and search for, I don't know, 4 first of all. Right? Okay. No, let's go ahead and search for 3. There we go. That's the key that we're trying to find. Now describe really quickly, at high level here, how would you go about going through this array and finding if that key exists? You'd start at the first element. Is that it? Is 4 it? Nope. Is that it? Nope. Is that it? Nope. Is that it? That it? That it? That it? Is that it? Yes. All right. So everybody here could, in fact, everybody here has implemented this already. All right. Do you remember Hack 7? What was one of the functions that you wrote in Hack 7? Contains, right? Something like this. Right? You did that, right? Okay. You've also done character arrays, right? Find character. There you were searching an array of characters, right? Instead of integers, you are finding characters, right? How many characters, right? That would be another question here. How many instances of X are there? Find them all, right? Because I want to remove all of those characters or something, right? Let's keep it simple though, and let's go ahead and think about an integer array. Right? What did that contains function look like? What's its input? The array, const int star array. I put a const in front of it. Why? Not going to change it. What else do I need to tell that function? What you're looking for, and also how big it is, the size. And here's my key. Okay. Now, when you originally wrote this function, we told you what it should look like. It returned an integer. Right? You can think of that as a bool, right? A boolean. It's going to return true if this array contains this key. It'll return false otherwise. So that's one way of doing it, right? So even with this specific answer, we're searching an array of integers for a particular element. There are still multiple variations that you can go through. For example, this function searches the given array, ARR, of size n for the particular key element. Right? Right. If found, it returns true. Right? Otherwise, returns false. That's what you did in Hack 7. Right? In fact, you did a couple of variations on that. What's an alternative? What's another variation on this? I don't want to just know if it's in there or not. I want to know, where is it? What would that be called? Get index or index of, right? Get index of, right? So if found, it returns, it returns the index at which it found it. Right? There's another variation. What do you think we should return if we don't find it? You can't return false, because false would be 0, meaning that I found it at index 0. It was the first one I found. That's not true. Right? Say what? -1 would be a good idea. -1 if no such element. Why -1? Because it's an invalid index. It's a huge red flag that this element does not exist, that you can easily check. What's another way that we could do this? If found, not index of, but, say what? We could do that if we did a different variation of, like find all instances of, or count, right? I want to look for a particular element here, though. Right? So it's C. How does C generally do things? There it is over there. What am I doing? Pointer, right? Pointer to. Right? And if found, it returns a pointer to the element. Right? What if we don't find the element? What would be a good placeholder there to say, that doesn't exist? Null. The only thing that you can, right? If no such element. Okay. 3 good ideas. 1 that you've already done, 2 that you probably haven't done. So let's do one of those. I'll let you choose. This one or this one? Pointer? Okay. So there's our choice. Let's go ahead and call it pointer2 or get pointer2 or something like that. What's my return type? Is it just a simple integer? No. If I'm pointing to an integer, what does it need to be? Pointer star. Okay. All right. How am I going to go about doing this? An idiomatic for loop. For I equals 0, I is less than n, I plus plus. If the ith element, array sub I, is equal to my key, then I found the needle in the haystack. I need to return something. If I get through the entire array and never match that key, what should I return? Null. Okay, good. So now what's that thing that I need to return? Could I return I? Well, that's the index at which you found it. That would be our second choice here. So that's not it. Is it array sub I? You can do that, but what are you doing? You give me 5. Okay, I found another 5 right here. I'm going to just give you back 5. Right? That doesn't actually solve the pointer issue. Right? So this is the element that you found. It's a regular old integer. How do I change it into a pointer to that thing? Ampersand. Excellent. So let's go ahead and test this. Int star pt p is equal to, what do I call it? Pointer 2. Right. Pointer 2, array, n, and key. Okay. Now you do some checks here. If p is null, that means that it was an unsuccessful search. If it's an unsuccessful search, that means it's not in there. Let's print that message. Could not find key value %d and the line, the key. Right. Else, we found it. Printf found %d, a key value %d at memory location %p, which contains value %d and the line. I'm going to print out the key, the original key, the pointer that I got back from that function for a memory address, and then finally I'm going to dereference the pointer so that I can get the integer stored at that memory location. Let's go ahead and compile this and see if it works. I'm searching for 3, right? Don't worry about that. It's a red herring. Right? Is it going to be a successful search or not? It should be. It's right there. Right? Found key value 3 at memory location blah, 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 which contains the value 3. Excellent. Let's go ahead and try it again. What about 4? I found key value 4 at memory location, whatever, 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 which contained 4. Which 4 was it? Probably the first one. Why? Because we started at the beginning and went to the end. So the first one that we find, right, that's the one that we want. So we end up doing this variation, the first instance of x. Right? If you want all instances of x, or the last one, then you need a different algorithm, okay? Or a different implementation. Okay, let's search for an unsuccessful search. Let's test for an unsuccessful search. Is 42 in that array? Nope, so could not find key value 42. It looks like it works to me, okay? Now what I want to do is I want to change the problem. Let's go ahead and create BRR and B key. 40.5, 42, let's go with 4.5, right? 0.5. Double and double. In other words, I want to search an array of doubles instead of integers, right? I want to change the variation. Everything else stays the same. We're still searching an array, but no longer in integers. We're searching for doubles, okay? So 4.1, 0.6, 5, 0.2, 0.1 again, 4.5, comma, 1.1, 3.9, 10.0. There we go. Am I going to be able to use the same solution here? Nope. A pointer to an integer is not the same thing as a pointer to a double. Right? But I could use almost the same solution. Copy, paste, pointer to. What will change here if you want to search an array of doubles? Well, now it's an array of doubles. What's your key value? A double, right? Searching for a needle in a haystack, or you're searching for an apple in a haystack, not an orange in a haystack, right? Apples and oranges. And if I'm going to return a pointer to it, I should be returning a double pointer. Right? Did I change a single line of code other than that? Nope, it will work this way. Well, it won't compile because I have pointer to and pointer to. So let's rename those. Pointer to for doubles. Right? Pointer to for ints. Right? What's the problem with this strategy? Now I want to do it again. Yeah, go ahead. No. Okay, all right, cool. Rubber duck debugging. Right? So now I want to do it for characters. Right? Copy, paste. Now I want to do it for airports. Copy, paste. Now I want to do it for teams. Copy, paste. Now I want to do it for all of these pieces of data times however many of these things I want to do it for. Right? So now I have to write hundreds of functions. None of them will be any different, right? Except for what they take as input and what they return as output. Right? Is it a good idea to start copying and pasting, copy pasting, copy pasting, copy pasting? Nope. Just like we only have one malloc for anything that you want, right? That's generic programming. You solve that problem, the general problem, and then you worry about specific implementations of it. So let's come back over here to my tablet here, and let's go ahead and start way at the beginning again and solve this problem starting with pseudocode, right? Generic, universal, abstract pseudocode. It's pseudocode because it's fake code. We're not going to use anything that is C specific. We're not going to use anything that's Python specific. That's why I'm writing it by hand, right? We're going to clearly label our input here a collection A of elements A1, A2, AN, and a key K. All right? And I'm going to clearly label my output here. An element A in A such that A is equal to K. Right? We're not done yet. Before I continue, though, I want to bring some things to your attention. Did I say that this thing was an array? Nope. Did I say that it was a list, a set, a hash map, a dictionary? Nope. I said it was what? A collection. I'm using abstract language here, right? I'm using generic language so that it can apply to any programming language and any data structure within that programming language. I gave them all names, but was I a self-respecting computer scientist and started my indexing at 0? Nope. I did it more mathematically. Mathematics always starts at 1, 2, n, right? But I did give them all labels. Did I have to pass in what the size of the array was, like I do in C? Nope. I encoded that by saying that there were n elements in that collection. Did I say that these were integers or doubles? Nope. I kept it generic. That's why this is fake code, right? It's pseudocode. Right? Did I use equals equals here? Nope. So I'm not going to use null, false, or -1 as indicators of an unsuccessful search. I'm going to use a math symbol. What is that thing, by the way? Say what? Oh, okay. The empty set would be more like that. Empty set 0. That's actually a good LaTeX lesson here. Right. So here's empty set. So here's 0 in LaTeX. 0. Right. Here is empty set. Empty set. There we go. If you're typing math in Word, first of all, stop and just do it by hand from now on. But the word empty set will look like a 0 as well, and it will look like phi, right? So here's phi. And what's capital phi? Yeah, looks like that. There we go. All right. So looks slightly different. But what I'm trying to get at here is just phi. It's just a placeholder symbol showing you that the search was unsuccessful. Right? And why do we use phi? Because it's used in math. Right? Phi if no such element. Right. Okay. It's just a symbol. Right? Some pseudocode will use nil instead of null. Right? Okay. There's no rules. Again, if there were rules, you'd have yourself a programming language. Right? Yet another programming language. Right? All right, so help me out here. How would you go about doing this? Just like we did in C. For each element A in A, I'm eschewing the traditional idiomatic for loop. For int I equals 0, I is less than n, I plus plus, right? I don't need an index variable. This is pseudocode. Right? There are some languages that allow you to use for each loops, right? Or enhanced for loops, whether or not you use the keyword for each, right? I'm doing that in plain English here. So plain English, math, right? Those are your tools for pseudocode. For each element A in A, if A is equal to K, right? Then output A. Exactly what we promised to do. Right? An element A in A such that A is equal to K. Otherwise, if you get done with all of that, you output phi. Okay? Now, another difference between, say, pseudocode and real code. Did I put, say, curly brackets around everything here, like we do in C? Nope, because that would be C specific. Not all languages do that. Anybody who's had Python experience, what would you put at the end of each of these? Colons. Right? I'm not going to put colons because this is not Python. Instead, what I'm going to do is something that you would never be able to code at all. These vertical lines that indicate the code blocks. Right? That this code block, that this if statement is bound to this part, that this for loop is bound to this part. Right? I really like that style for pseudocode. Again, it's just a style thing. I really like it because there is no way for you to ever type that out, right? Unless you're using LaTeX, and then I stole this from LaTeX, right? Which does have rules for typesetting pseudocode, making it a programming language technically, but nobody's going to program in LaTeX, right? All right. I didn't say return. Why? Because this is not a function. This is pseudocode. There's our algorithm. I'm going to go ahead and move this down and give myself some room there, okay? Because we're going to come back to it and give it a name. The name will be based on how efficient is it, right? So how efficient is our search algorithm? So to answer the question of how efficient is it, first of all, you need a measure of what it does, right? So what work or resources does the algorithm consume? Right. So in the real world, what resources do algorithms consume? What resources do computers consume? Okay, RAM, that's memory. Right. What else? Clock cycle, so cycles equals time. Right. Power, good. Power, right, equals power. Right? Any Bitcoin miners? No? All right, well, I mean, there aren't that many dorms here, right? but you're not charged an electrical bill. You're really missing out on a
They yell at you.
Ah, okay. That's what I thought. There, you didn't raise your hand when you. So apparently you have tried.
No, someone else did.
Oh, okay. So, yeah, not me. Right? If you're not paying the power bill, then then mine all you want, right? So power, right? Those are real world engineering concerns. And as an engineer, those are important, right? But when we're looking at an algorithm from an abstract point of view, from a mathematical point of view, what we like to do is we like to simplify, right? What operations does it perform? We call this the elementary operation. Why? Well, if you're actually, performing this in the real world, that operation is going to take some memory. It's also going to take some time, and it's certainly going to take some power, right? So if we simplify it down to just this elementary operation, we basically capture all of these ideas in one, right? So let's take a look at this algorithm again and tell me, what operations are we performing here? Let me go ahead and number the lines. 1, 2, 3, 4. Let's go top to bottom. For each element in A, you're doing some work to iterate over the elements. If you were actually in a program, for example, over here, right, you're doing 3 operations just to do that. You're only doing this one once at the beginning of the loop, right? But you're doing this comparison to see if you should be continuing with the loop every single time. And you're doing this addition, +1, +1, +1 every single time. So you're doing an assignment, you're doing a comparison, you're doing an addition, 3 different operations. We generally don't like looking at those, though, with respect to an algorithm, because implicitly, somewhere in that loop, you're doing other work, right? So for each addition to in your for loop here, you're doing whatever operation you're doing inside this loop anyway. So if you just simplify it and count whatever's inside this loop, you're capturing the idea of that work as well, right? Simplify, simplify, simplify. So I'm not going to look at that first line. I'm going to look at what we're doing inside that loop. Now let's jump ahead here to line 3. Do we always do that line? Nope, we only do it once, and that's at the end of the algorithm. So what are we doing for every single iteration of this loop? A comparison. Right? So our elementary operation will be the comparison on line, what was it? 2. Right? Now, if you had a different algorithm that didn't have any comparisons, it only had additions, then you would focus on those. If you had an algorithm that did additions and multiplications, you probably want to look at the multiplications because those are more expensive. If you had a different algorithm that was traversing a graph or something, your elementary operation would be traversing from one node to the next because you're traveling or something, right? For this particular algorithm, that's what we're going to focus on, line 2, right? Now the question becomes, how many comparisons does our algorithm perform? Right? I'm going to give you a hint here, and we're going to say, assume the input size is n. There are n elements in A. Okay? So let's take a look. Sometimes you get lucky. You search for 4, and you find it in the first place you find it. Sometimes you don't get lucky. You search for 42, and you end up searching the entire array and don't find it. Sometimes it's halfway in between those two things. You search for 9, right? And you get away with 1, 2, 3, 4 comparisons. So let's generalize this. What about the best case scenario? Best case scenario, how many comparisons does our algorithm perform? You said, I heard it, 1, right? You get lucky and that's the first place that you find it, right? That our element A of 1 is equal to K, right? The first element. What about the worst case scenario? Yeah, no, you don't. So you find it in the last place that you look for it, right? At the very end here, a sub n, or it doesn't exist, and you end up making how many comparisons to return phi here? So how many comparisons do you make to say that that's not it, that's not it, that's not it, that's not it? Among these n things, none of them was it. N comparisons. All right, well, sometimes, I mean, you can't assume that you'll always be lucky. You can't assume that you'll always be unlucky. So maybe you look at it from an average case. The naive way of looking at this is to simply just take those two averages, n plus 1 all over 2, right? Which I will simplify here to n over 2. This is the naive approach. If you want the real approach, you need to define a probability distribution on the successful search, count up the number of comparisons, maximize that, and once you've done all the math, guess what answer you come out with anyway? N over 2. Right? So that's the naive way of looking at it, but the other way of looking at it is n divided by 2. Let's graph these. There we go. What I'm going to graph is n. This is the size of the collection. And I'm going to graph it with respect to time, right? You can measure it in nanoseconds, minutes, it doesn't matter what your scale is, okay? What I'm going to do is, or time slash number of comparisons. You know what? I don't have to write sideways. Time slash number of comparisons. There we go. Come on. Cut. Paste. Rotate. There you go. I don't know if that was quicker than just doing this or not, but it was cool. All right, so let's graph the worst case scenario here. What would that graph look like? Again, a worst case scenario is n. So it's going to be, and it should snap to 45 degrees. Come on, there, snap to 45 degrees there. N, right? This is the worst case. What about the best case? Or not the best. Well, yeah, sure. What about the best case? What's it going to look like? It's a straight line like that. I'm not even going to bother with that. Right? That does not give a realistic impression of how this algorithm performs. Right? What about the average case? Half. So the slope will be 1/2, cutting right about there, let's say. Right? This is going to be the average case. Right? And this is n divided by 2. Okay. So if your scale here is in millions, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There we go. 10 millions. Right? Then the number of comparisons here, the time, whatever, you can go ahead and benchmark that and come up with an actual value. What I want to note here is what kind of functions are these? N and n divided by 2. Most of you are in calc, since we're all engineers here. So tell me what tool you use to determine what the growth rate of a function is. The first derivative, right? The growth rate of a function. You use the first derivative. Right? So what's the first derivative of n? Remember, n is my x, right? So it's 1, right? That's probably the first derivative that you ever learned, right? Of a polynomial? Yes? No? What's the first derivative first derivative that you ever saw? X? There you go. So this one, right? What about 1/2 n for that first derivative? It's on both of them. It's not a product rule or anything here. Just 1/2. Okay? So tell me about these two functions. In other words, what's the growth rate of both of these functions that I just graphed? These are both constant. Right? Constant growth rate. In other words, they both have the same growth rate. Now characterize those functions for me. What kind of functions are these? So the x, and then there's a different coefficient, 1/2 x, right? For nomenclature here's a hint. What kind of function is this? A parabola, that's the shape. What kind of function would give you that, though? Or n squared, x squared, right? And what do we call that? A quadratic, right? That's a quadratic function. So if we call them things quadratic functions, what do we call these things? They're linear, right? Both are linear functions. And now we have a name for our algorithm. What do we call it? Linear search. It's called linear search because regardless of the worst case or the average case scenario, it is going to perform a linear number of operations with respect to the input size. Right? Let's look at that from another perspective. You can take your calc hats off now if you want. Right? And let's just use our algebra hats here. Okay? If I have an input n, right, and say that I double the input size, 2n. So in other words, I go from 1 million to 2 million elements in my array. Suppose that it took t time before, right? 5 seconds, 10 seconds, it doesn't matter, right? It just takes t time. What is my time now that I've doubled the input size? Double t, right? 2t. Why? Because if I go from 1 to 2, right, then from the perspective of the average case scenario, you've doubled your value, right? You've gone from 1 up to 2, roughly, right? I didn't write it correctly, but whatever. With the worst case scenario, you went from, say, whatever time this was, I guess 1 up to 2 here. 1/2 over, whatever. The magnitude has gone up the same, okay? What if I did it even more? What if I went from, say, 1 million up to 10 million? And again, suppose that it took time t before. How much time does it take now? 10t, right? So increasing the size increases the resources or time linearly. Whatever your factor is over here, right? Your multiplicative factor 2 or 10 times as big or 100 times as big. You're going to be paying that much more in time and effort and resources, memory, power, whatever, right? All right, can we do better? So, I don't know, here's a gold bar. Or it's my placeholder here for a prize. Right? So there's a show that's still on. I'm sure that it's in the Zeitgeist. Everybody knows what it is. Price is Right. Right? So there's this prize here, and they'll tell people, well, it's between $1 and $100. And if you can guess the price of this thing right here correctly, you win the prize. Now, you can make as many guesses as you want, but you only have a certain amount of time. Right? We'll give you some more information. If you guess like X dollars, what we'll say is, all right, that's larger, or that guess is too low, or that guess is too high. Hopefully, this sounds familiar. You programmed this in like week 4, right? The guessing game. I'm guessing of a number between 1 and 100. What is it? What was your strategy for doing that? I'm thinking of a number between 1 and 100. What's your strategy? What are you going to guess first? All right, the middle. In this case, it's going to be about 50. Why? And now I'm going to tell you that it's actually lower. Why does that help you? You cut your answers in half, exactly. Right? So instead of asking, oh, is it $1, is it $2, is it 3, 4, 5, 6, 7, 8, 9, 10, da, 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 right? You have now cut down 100 choices, right, down to only 50 choices, minus the one that you just got wrong. Okay? All right, continue. I am thinking of a number now between 1 and 50. What is it? All right, you're going to guess 25. Now you're between 25 and 50. All right, technically 26 and 49. Keep going. By the way, the number that I'm thinking of is higher than 25. 38. All right, that's about in the middle. 38 and 50 higher. And by the way, keep track of how many you've guessed. 1, 2, 3. Right. 40. Good. Who said 42? You did. Why? Exactly. That's my go-to number. Why did I use 42 over here? Right? Those are just nerd numbers, right? All right. So you got it in 3 guesses, or I guess 4 guesses to get that last one. All right? That relied on 2 things. That relied on all these numbers being in order. Actually, 3 things. It relied on these numbers being in order. It relied on the fact that you could jump to the middle easily. And it relied on the fact of additional information of, nope, it's lower, or nope, it's higher. All right? So now what I want to do is I want to give you an array to search. Let's see. Nope. Go back all the way to CS1. Where is my sorted array? There we go. Okay. There's your sorted array. All right. Those 3 things that I said that we need it to be in order. It is in order, right? It's sorted. We can easily jump to the middle element. How? Well, if I told you that there were 11 things in here, what is the index of the middle element here? N divided by 2. And take the floor or integer truncation here, because do you see a an index that's equal to 5.5? Is that an index that you've ever heard of? Nope. So what we'll do is we'll rely on integer truncation to get us down to 5. That one right there. All right. Now, what are you searching for? Well, we didn't start out here, I guess. Let's search for 42. That was my intention, actually. All right. So we're not going to search for, we need to search for 42. We check the middle element here, and we see that it's 12. Is that the thing that I'm looking for? Nope. So where is the thing that I'm looking for without having to look at all the elements? It's higher. Right? So all I have to do is focus on a subarray now from 6 up to 10. Right? And continue. Right? So exactly, recursion. Right? Recurse on 6 to 10. What is the middle index of 6 and 10? 8. How did you get that? Yeah, how do I get the middle index here? Middle index. Right. Okay, yeah, 10 minus 6 divided by 2. That gives you the size of that range, right? That's going to be 4 divided by 2 is going to be 2. Well, that's not the index, because that's over here, right? But it's 6 plus 2, right? Let's figure that out math-wise. Right? If this is L and this is R, then it's going to be L plus R minus L over 2. Right? That's the math that we just figured out, generalized. What's an even better way of doing it? There you go. Average. L plus R over 2. Right? And then, of course, truncation here, because you are dealing with whole numbers here. Right? So the middle index then ends up being 8. And you ask the question again, is 8 equal to 42? No. So where's 42 if I'm going to search for it? It's lower. And now I can focus on that part of the array. Right? And now I'm at 6 and 7. What is the middle index here? What's the average of 13? 6.5. Integer truncation becomes then 6. Right? And so there's my middle index. Is 34 equal to 42? No. So where 42? Where is 42 if it exists? 7. All right. So I've narrowed in to just this one element now. Now I ask, what's the middle? So now we've got 7 and 7. What's the average of 7 and 7? 7. And guess what? You find it right there. Done. What if we didn't find it? What if we were searching actually, say, not for 42, but for 41? We would get down to this one element, and we would say, well, that's not it. It's lower. And so what ends up happening to our range here? It becomes like this, right? They've crossed each other. Does that sound familiar? Your lab on Tuesday, right? You start one at one end and one at the other end, a left and a right index. You move one in, you move one in, you move one in, you move one in until they've gone past each other. At which point you know that there's no such element of 41 in this array. This entire process is called binary search. It's called binary not because of binary, numbers or anything. It's called binary because you cut the input in half. Okay, each time. So I want to start out. Maybe we'll get through it today. I don't know. Let's go ahead and write pseudocode for exactly what we just did. This situation where we start at one end and we start at the other end, and then we jump to the middle and we determine, oh, well, it's in this half or it's in this half. Let me go ahead and give you another picture, a generalized picture of that, so that we can design our pseudocode. Here we go. There we go. Is that the generalized one? Yeah, that's as good as I'm going to get. At least I should have copied the other one, right? So if it's sorted, then it looks like this, right? That all I have to do is look at the middle element here, n divided by 2, and that's my middle element here. Everything that here is less than m, and everything over here is greater than m, right? Whatever element is stored right here, okay? That means that I can recurse on this half, or I could recurse on this half. Let's go ahead and write a recursive version of binary search to begin with, right? And then we'll improve it by taking away the recursion, just like we did with memoization. My input here is going to be several things. A collection of elements. A equals A1, A2, AN. A key. That's exactly the same as linear search. We're solving the same problem, but with a different algorithm, right? And a left index, I'll call it L, and a right index, I'll call it R. Right? So in other words, I call this function binary search, passing in A, K, L, and R. There's my annotation of it, right? So I'll put this as a comment, right? My output will be, say, an element A in A, such that A is equal to K, the key element, K. Now I'm saying an element here because there could be many different ones. Are you finding the first one? Are you finding the last one? Are you finding all of them? That's a different question, right? That's a way more specific question, and that's not the one that I want to answer. I just want an element. Any element will do, right? Now let's codify this. Right? What am I going to first do? I'm going to compute that middle index. M. Here's another piece of pseudocode. L plus R over 2. Did I use the equals operator here? Nope. Because it's math. Equals doesn't mean take the thing on the right-hand side and put it into the thing on the left-hand side. This arrow does, though, in pseudocode. Not all languages, by the way, use the equal sign. Right? Has anybody used MATLAB before? Or not MATLAB, Maple? No? Okay. Maple and I think maybe Fortran or COBOL or something, their assignment operator looked like this. A colon and then an equals. Has anybody used Haskell? Probably even fewer answers there, I'm sure, right? A less than and then a hyphen is their assignment operator. Hey, what does that look like? An arrow, right? So I've computed the middle index, right? This is the middle index. Okay. Now I've got some choices, right? I want to first know, is that middle guy the thing I'm looking for, right? If A sub M is equal to the key that I'm looking for, I'm done. Output A sub M, right? Because I found something that matches the key. Else if the thing that I'm searching for, K, is less than A sub M. Where do I need to search for it in this array? The thing I'm searching for is less than this guy right here. So I would need to search in the left half. What do I need to update my indices to? Right, so binary search. The collection doesn't change. The key doesn't change. The left index doesn't change because I want the left is over here, the right is over here in general, right? And the middle index is right here. So I should update my right index to be this guy. Why not this guy right here? I just checked them on this line right here, right? So I will take it and I will subtract 1. Right? Else, if the thing that I'm searching for is greater than the middle element, where do I go next? Binary search of A, K, L plus 1, or sorry, what am I doing? R minus 1. It should be M minus 1. There we go. And then M plus 1 and R. There. Okay. Now why plus 1 again? Because if I need to search this half, should I bother looking at this element again? No, I just looked at it. Right? So I update my indices so that I'm only looking at this half. Or I update my indices so I'm only looking at this half. What's one thing I forgot to do, though? Is the what? If it's not there at all, right? When you're designing a recursive solution, what's the first thing that you should do? Base case. That's what I didn't do. So we'll do that next. Yeah, go ahead.
So when you do the middle plus 1, middle minus 1, because you already looked at the middle one, that takes some processing time, right? So
Yeah, that's a subtraction. That's an addition.
Okay, so then, is there a break-even point between using a little bit of subtraction and addition versus just look at the same index again?
Probably not. Certainly there's a non-trivial amount of extra work, but it's there is a trivial amount of extra work, right? In the grand scheme of things, it's not going to matter. But we haven't analyzed this yet, right? So the speed up with this algorithm is going to be exponential. One piddly operation is not going to matter in the grand scheme of things. We're going to end up having an exponential speed up because of this itself. All right, so I do need to give myself some more room here. Move this down a little bit. And what should be my base case here? If the left index has exceeded the right, well, what if they're equal, by the way? If they're equal, you still want to go and see if that's the guy that you're looking for, just like we did with this 42 right here, right? All right, so if the left index is, I don't want parentheses. There we go. If the left index is greater than the right index, that means that you've passed each other. And I'll output phi. Right? Phi if no such element. Okay? That's a recursive version. We won't fully analyze this because to analyze this, usually what you have to do is bring in the master theorem, or you have to bring in some math. I'll bring in a little bit of math, but I won't do the full analysis of this. Right? What I'll do instead is I'll write up a table here. Right? So suppose that the input to start out with here is n. Right? The worst case scenario is going to be exactly the same, where you don't find what you're looking for. And you end up having to move these indices back and forth, back and forth, back and forth until they've gone past each other. When the input is n, the number of comparisons that you make of comps to make is 1. Because all you have to do is this the guy that I'm looking for? And no, it's not. So then you need to go in this half of the list, or you need to go in this half of the list. Now, technically, you might be saying to yourself, well, wait a second. This pseudocode actually has 1, 2, 3 comparisons, right? You could get rid of this entirely with just an else statement. Else statement. Why? I wrote this explicitly so that you would know what you're actually doing with this case. Right? That's not necessary. It's either equal, strictly less than, or strictly greater than. It's one of those things. So you don't have to have this condition right here. So now we're down to 2. Right? 1, 2. Those really aren't the same. Or those really aren't different, I should say. Right? When we ultimately go to program this and implement this, we'll be using what's called a comparator. That comparator will be one function call. And then whether or not you go left, right, or you're done, right? That's kind of like us counting, and my code spaces is gone now, but that would be kind of like counting those values that we incremented and compared to in the for loop of the linear search, right? Those are necessary for the control structures of the algorithm, and we're not going to count those. I'm going to roll these 2 comparisons into one comparison. We do one comparison to cut the input in half, right? Okay. We do one more comparison to cut that in half again. N divided by 2 cuts in half, n divided by 2. Tell me what math that is. Simplify that. N divided by 2, then divided by 2 again. 4. Right? We do one more comparison to cut that in half. N divided by 4 by 2 is equal to 8. Right? One more comparison to cut it down to whatever. Right? Do you see the pattern here? It's exponentially being cut in half. Right? 1/2, 1/4, 1/8, 1/16, 1/32, etc., etc. Right? When do we stop? When what? When you get your answer, sure. Right? I could have gotten lucky and found it in the third place that I look for, right? I'm not going to get lucky, and I'm going to go all the way down to when the array is of size 1. I'm down to one element. Is that the thing I'm looking for? And I make one more comparison to say no or yes. Yes, that's what you're looking for. You found it in the last spot that you looked. Or yeah, no, that's not there, and return phi. It's an unsuccessful search. How many ones are there? 1 plus 1 plus 1 plus 1 ... plus 1. Right? So to answer that, I'm going to ask what value of k gives you 1. Right? In other words, n divided by 2 to the k is equal to 1. Right? Why are we interested in that? Because k is going to be let me go ahead and write it out explicitly here. K is going to be 0, 1, 2, 3, ... and then k in general, and what k gets me to the end here. Right? K is the exponent. All right, this is just simple math. N is equal to 2 to the k, good. How do I solve for k now? Log, right? But not log base 10, log base 2, because we're now back to being respectful, self-respecting computer scientists, not mathematicians and not the normies that have 10 fingers and 10 toes, right? Right. Okay. There we go. Our base is 2, right? Everybody else's base is 10 because they count in base 10. What is a mathematician's base, by the way? Oh, not 1. The natural log of e, or natural log of x. The mathematician's base is what? E, right? Why? Why? E is 2.71 blah 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 blah, right? It's what? It's some ratio. Well, something special happens with it. Again, put on your calc hat. There you go. Where the derivative ends up being the derivative on the entire thing here is what? E to the x. It stays the same. Right? That's the point at which the derivative stays the same. It's the point at which the first derivative of natural log stays the same as well. Well, the derivative of natural log is 1 over n. Right? Nice and clean, no coefficient. A coefficient of 1, basically. Right? There is a coefficient out here. It just happens to be 1. Why? Because the coefficient is the natural log of e, right, which is 1. And now you understand why mathematicians are obsessed with e, because it simplifies all their formulas. Not that it has any bearing on reality. Right? Okay? And it does, in that you can always convert from one base to another. Right? Cool. That's the complexity of the algorithm. Right? Binary search. In the worst case, performs log n, log base 2 of n, comparisons. How much better is that? Well, let's go back to our graph here. Come on. And snap to 45 degrees. Right? There's the worst case running time of linear search. Linear search. What does a logarithm look like? Yeah, it curves off and grows extremely slowly. Right? I wonder, can I do that smooth? Oh, nice. There we go. There's log n. Right. It's going to be exponentially faster. Exponentially faster. Why? Because to go from n to log n, right, that's an exponential speed up. The last thing that we'll do today is look at this from the perspective that we looked at before. What if I go from, say, n elements to 2n elements? And before it took log n time. Right? Now it takes what? Log 2n time. Right? It doesn't take twice as much time, right? It takes, the input is twice as big, but the time it took is only log n, right? And so we've got log 2n here. Now, pull out your trig hat. Where do you do log identities? Algebra? All right, pull out your algebra hat, right? And tell me how I can simplify this. No? Log, yeah, a log of AB is equal to log of A plus log of B. Right? So log, and I'm going to switch them immediately here and go log of n and log of 2. What happens to that second one? It disappears. Well, not entirely. Plus 1. In other words, if you went from 1 million elements to 2 million elements, right, you don't have to perform up to 2 million more operations. You only have to perform one more operation, right, because of this exponential speed up. Right? If you went to, say, 10n, that would end up being log of 10n. Same log identities here, right, plus log of 10. If you went up an order of magnitude, what is log base 2 of 10? 3 point something something. We'll just say that it's log n plus 4, right? You only need to do 4 more comparisons, right? 10 times as big. If you go from 100 million to 1 billion elements, you just need to do 4 more operations, right? Now, what's the, oh yeah, go ahead.
You have to sort out this first.
That was my last question here, right? So, what do you got to do first? Yeah, you got to sort it, right? And that's what we'll look at on Tuesday after the break. Remember that there is no class and there is no lab on Tuesday next week. All right. I'll see you in Hack.